This question is about reactions of ions and compounds of transition metals. Part A. A student carries out 2 experiments on a solution containing CrH2O 3 aqueous. Experiment 1. The student adds an excess of aqueous ammonia to a solution containing CrH2O 3 aqueous until a purple solution is formed. Experiment 2. The student carries out the following reaction sequence. Step 1. NaOH aqueous is added slowly to a solution containing CrH2O 3 aqueous in a boiling tube. A grey-green precipitate forms. Step 2. An excess of NaOH aqueous is added to the boiling tube. The precipitate dissolves and a green solution forms, containing a 6-coordinate complex ion. Step 3. H2O2 is added to the mixture and the boiling tube is heated. A yellow solution forms. Step 4. The solution in the boiling tube is acidified. The solution now contains Cr2O7 2- aqueous. Part 1. What is the formula of the complex ion in the purple solution that forms in experiment 1? To answer this question, it's important to know the equation for experiment 1. So what's happening in experiment 1 is CrH2O 3 is being reacted with 6 ammonias or NH3s. And that's going to produce the complex of CrNH3 3 plus 6H2O. And therefore that would make the complex ion in the purple solution that forms in experiment 1. That would be our CrNH3 3 and this would be an aqueous solution if we wanted to add a state symbol. To get the mark for this question, you must write CrNH3 square brackets 3 plus. The aqueous state symbol is optional. It doesn't get you the mark. It won't deduct the mark if you don't have it, but it is nice to include it. Part 2. Suggest an equation for the reaction in experiment 2, step 1. Include state symbols. So if we look at step 1, we've got NaOH aqueous and CrH2O 3 aqueous. So these are going to be our reactants. So if we wrote this on our answer line, we would have CrH2O 3 plus 3OH minus aqueous ions. This is the part of NaOH that we're going to react. And this would produce the precipitate is going to be a grey-green precipitate. So we are required to know our colours of our transition metal complexes. And that would be CrH2O OH3, and that's going to be a solid because it's a precipitate. And to balance the equation, we would have 3 H2Os produce, and they would be liquids. So write liquid as its state symbol. Finally, to finish, we need to add our aqueous to our transition metal complex we started with, our CrH2O 3 plus. We're told in the question it's aqueous, we just need to include that now. This question requires you to know about transition metal complex colours. So the reason you have 3 OH minus ions in this equation is because you are going to produce a grey-green precipitate, and that is your CrH2O3 OH3 solid. That has a grey-green colour and is a solid, so it's precipitate. And therefore that's why you need 3 OH minus ions in this equation. To get the mark for this question, you get the mark for having the full correct equation for this reaction and the correct state symbols for this reaction. Part 3. Draw a 3D diagram for the shape of the complex ion that forms in experiment 2, step 2. Include the charge of the ion. So in step 1, we formed the complex CrOH3H2O3, and this had a neutral charge, and it was a precipitate, and it was solid. So then when we're reacting excess NaOH, we're going to replace our remaining H2Os with OHs, and we're going to produce CrOH6, and this is going to have a 3- charge because chromium has a 3+ charge. Each OH has a minus charge, and so it would give an overall charge of 3-, which we can write as the overall charge for our complex. This is, we're told in the question, a 6-coordinate complex ion. So it's going to have an octahedral 3D arrangement. So that means we're going to have chromium, we're going to have 2 lines, and then we're going to have some wedges. So we'd have dashed wedges, and then we're going to have some solid wedges. And then attached to each of these wedges, we're going to have an oxygen, and attached to each oxygen will be a hydrogen. So we'll have OH attached to each wedge, making sure that it is the oxygen that's attaching to the wedge and not our hydrogen. So once we've finished this, we've completed this part of the question. To get the marks for this question, you get a mark for having the correct 3D arrangement for CrOH6 3-, and then you get your other mark for having a 3- overall charge. These 2 components get you your 2 marks for this question. Part 4. What is the formula of the ion that causes the yellow colour in experiment 2, step 3? The reaction for step 3, or equation, would be our 6-coordinate complex ion, CrOH6 3- plus H2O2, and that's going to produce our CrO4 2-, and this is a yellow solution, and we're also going to produce 4 H2Os, and this balances the equation. Therefore, the formula of the ion that causes the yellow colour, well, that is going to be our CrO4 2-. So we write this on the answer line. To get the mark for this question, you must write CrO4 2- to get the mark. This reaction is a result of the chromium being oxidized from Cr3+ to Cr4+ by hydrogen peroxide, which is a strong oxidizing agent. And this is a little bit of an explanation as to what this equation is showing. Part 5. State the colour of the solution that forms in experiment 2, step 4. So this question is asking us to recall the colours of transition metal ions. And so the colour that we need to identify is the colour of our Cr2O7 2- ion. And the colour of this ion is an orange colour. This is something you need to know for this syllabus, and so if you didn't know it already, I'd recommend making a revision resource because this is a recall question. To get the mark for this question, you must write orange on the answer line provided. Part B. Vanadium ions have 4 common oxidation states. Table 18.1 shows the colours of the ions in aqueous solution. Part 1. Complete the electron configuration of a V3+ ion. Firstly, let's write the electron configuration for vanadium. So that would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. And then we're asked for a V3+ ion, so that means it's going to lose 3 of its electrons. So the 4s electrons, they're filled first, but they're also lost first. So we're going to lose both of these 4s electrons and then one 3d electron. So that would leave us with the electron configuration for a V3+ ion as 1s2, 2s2, 2p6, 3s2, 3p6, 3d2. To get the mark for this question, you must have the correct complete electron configuration for a V3+ ion. So 1s2, 2s2, 2p6, 3s2, 3p6, 3d2. Part 2. The student adds excess iron to a solution containing VO2+ aqueous ions and observes that the colour of the solution changes from blue to green and then to violet. Use the relevant standard electrode potentials shown in Table 18.2 to explain these observations. So firstly, what we want in this question is we're told that an excess of iron is added to a solution containing VO2 plus aqueous ions. So that means we need to look at the ion equilibrium or redox system, and we want the iron. So that means we want this equilibrium system to go backwards or shift to the left. And then we want the VO2 plus ions. So we're looking at the two that contain the VO2 plus ions, and we want the equilibrium to shift forwards. So that means we want it to be more positive, and if we are shifting forwards, because it's more positive than our negative 0.44, this +1 would shift forwards also, and we don't want that because for this one we want it to shift backwards so that we start with our VO2 plus. So that means we're going to react redox systems 2 and 4 together, and that is because we want to start with Fe and VO2 plus. So we want equilibrium or the redox system 2 to shift backwards so that we can start with our Fe, and we want equilibrium system 4 or redox system 4 to shift forward so that we start with VO2 plus. If we were to use redox system 6, this would shift forwards, and so we would end with VO2 plus, and we would start with VO2 plus, but the 2 would not be a part of the charge. It's like an O2. So that means we're going to go from VO2 plus to V3 plus. And so the colour change for this reaction will be creating a green solution. And we know it's a green solution because, referring back to table 18.1, we can see that the V3 plus ion is green. And we're starting with our VO2 plus, and which is blue. So we're doing a blue to green colour change, which we could also write here. So it's a blue to green colour change. Then if we look at the redox systems with V3 plus, we have redox system 4, and then we've got redox system 3 as well. And in redox system 3, we've got a V3 plus going to a V2 plus. This is our next change. We can write our V3 plus goes to V2 plus, and then we need to talk about the colour change. So looking at table 18.1, the colour change from V3 plus to V2 plus, well, that's going to be a green to violet colour change. So we can write this. It will be a green to violet colour change for redox system 4 and redox system 3. Now we need to explain the reasoning, and the reasoning is because the electrode potential of system 4, I'm using system 4 as an example, and system 4 is VO2 plus to V3 plus, and what it is it's more positive than redox system 2. And so what this is going to mean is that the Fe2 plus to Fe redox system is going to cause the equilibrium of system 4 to shift right. So if we write this, this is going to explain why our colour change are what they are. And so to get the marks for this question, you get a mark for describing the correct colour changes. So both colour changes get a mark. Then you get your second mark for talking about the electrode potential of system 4 being more positive than system 2. And then you get your third and final mark for saying that the equilibrium shifts right, and this is the equilibrium shifting right for system 4. So all of this gets you your 3 marks for this question. Part 3. Construct an equation for the first colour change from blue to green. Firstly, we need to rewrite the equilibriums for redox systems 2 and 4 because we're talking about the colour change from blue to green, and this involves redox systems 2 and 4. So rewriting redox system 2, we've already identified that the equilibrium is going to shift to the left because it's going to go backwards because it's got a more negative electrode potential. So if we were to rewrite this, we would write Fe goes to Fe Fe2 plus 2 electrons. And then rewriting redox system 4, we've identified that this shifts forwards because it's got a more positive electrode potential. So we would rewrite it as VO2 plus 2H plus an electron goes to V3 plus H2O. And then we've rewritten both redox systems in the correct format. However, we want the overall equation, so we need to scale up redox system 4 by balancing the electrons. So we want 2 electrons, and that means we want 4 H pluses, 2 VO2 pluses, 2 V3 pluses, and 2 H2Os. And then if we cancel out the electrons, because we've got the same number and anything else that's balanced, in this case nothing else is the same, so we can't cancel out anything else, we've then made our overall equation. So that would be Fe plus 2VO2 plus 4H plus goes to Fe2 plus 2V3 plus 2H2O. And so we've now written the overall equation for this first colour change. To get the marks for this question, you get the marks if you've got the correct overall equation for this first colour change from blue to green. Part C. Iron 2 gluconate C12H22FeO14 is the active ingredient in some brands of iron supplements. A student carries out an experiment to determine the mass of iron 2 gluconate in 1 tablet of an iron supplement using the method below. Stage 1. The student crushes 2 tablets and dissolves the powdered tablets in dilute sulfuric acid. Stage 2. The student makes up the solution from stage 1 to 250.0 centimeters cubed in a volumetric flask. Stage 3. The student then titrates 25.0 centimeters cubed portions of the solution obtained in stage 2 with 0.00200 moles per decimeter cubed potassium manganate 7. The student obtains a mean titer of 13.50 centimeters cubed. In this titration, 1 mole of manganate 7 ions reacts with 5 moles of iron 2 ions. Part 1. Explain why the student used 0.00200 moles per decimeter cubed potassium manganate 7 solution for this titration, rather than the more usual concentration of 0.0200 moles per decimeter cubed used in manganate 7 titrations. The reason for this decision is because 0.00200 moles per decimeter cubed solution gives a larger titer, so a smaller percentage error. To get the mark for this question, you must write this statement, that a 0.002 moles per decimeter cubed solution gives a larger titer and therefore a smaller percentage error. And that's the reason the student's using a smaller concentration of potassium manganate 7 solution rather than the more usual higher concentration. So the theory behind this answer is the equation triangle of NV times C. So what this equation triangle is showing is that for a given number of moles, a smaller concentration needs a larger volume of solution. Hence why a larger titer is created, and that means there's a smaller percentage error. Part 2. Use the student's results to determine the mass in milligrams of iron 2 gluconate in 1 tablet. Give your answer to 3 significant figures. The first thing we're going to do is highlight the useful information in this question. So that would be the formula of our iron 2 gluconate, the fact that the student is crushing 2 tablets, the fact that we're making the solution up to 250 centimeters cubed, but using 25 centimeter cubed portions, so that's a times 10 we need to factor in, and the concentration of our potassium manganate 7 solution and the titer that is obtained. So firstly, we're going to calculate the moles of MnO4-. And we're going to use the equation triangle of moles divided by volume times concentration. So working out moles, that would be 0.002, which is our concentration, times 13.5 times 10 to the negative 3 because we're converting centimetres cubed into decimetres cubed, and we do this by dividing by 1,000 or timesing by 10 to the negative 3. And that gives us 2.7 times 10 to the negative 5 moles of MnO4 minus in our solution. And then we need to work out the moles of Fe2 plus. We're told in the question that 1 mole of manganate 7 ions reacts with 5 moles of iron 2 ions. So that means to work out its moles, we do 2.7 times 10 to the negative 5 multiplied by 5, and that gets us 1.35 times 10 to the negative 4 moles of Fe2 plus in 25 centimetres cubed. And we want in 250 centimetres cubed, so this is where our factor of 10 comes in, because we do 1.35 times 10 to the negative 4 times by 10, and that gets us 1.35 times 10 to the negative 3 moles of Fe2 plus in 250 centimetres cubed. And so now we've got the moles of both our manganate 7 ions and our iron 2 ions. Now we're going to use another equation triangle, and the equation triangle we're going to use is mass divided by moles times relative formula mass. And we're going to use this to work out the mass of iron 2 gluconate in 1 tablet. It's important that it's 1 tablet because we are crushing 2 during this experiment. So we need to divide by 2 at the end. But firstly, using this equation triangle, we would do 1.35 times 10 to the negative 3 multiplied by the relative formula mass of our iron 2 gluconate. So this is 12 times 12, because that's the relative formula mass of carbon, and we've got 12 of them, plus 22 times 1, because we've got 22 hydrogens and its relative formula mass is 1, plus 55.8, because that's the relative formula mass of iron, and then plus 14 times 16, because we've got 14 oxygens and its relative formula mass is 16. That equals 0.6018 grams in 2 tablets. So this is 2 tablets worth, and we need 1 tablet. So we would divide by 2 and we get 0.301 grams. That's 3 significant figures, and it's 1 tablet. But we want in milligrams, and that's what we're told in the question. We want milligrams and 3 significant figures. So working out milligrams, this would be 301 milligrams, which is what we write on the answer line for this question, 301. To get the 5 marks for this question, you get a mark for working out the moles of MnO4 minus, a mark for working out the moles of Fe2 plus in 25 centimetres cubed, a mark for working out the moles of Fe2 plus in 250 centimetres cubed, a mark for working out the mass of 2 tablets, or the mass of iron 2 plus in 2 tablets, and then your final mark comes from working out that it's 301 milligrams of iron 2 gluconate in 1 tablet. Writing this as 3 significant figures, writing 301 gets you your 5th and final mark. Part 3. Some iron supplements contain iron 2 sulfate or iron 2 fumarate. The information in table 18.3 is taken from the labels of 2 iron supplements A and B. Choose which iron supplement A or B would provide the greater mass of iron per tablet. What we're going to do is work out the ratio of iron in each compound first, and then we're going to multiply it by the mass of iron in milligrams. So for supplement A, working out the composition by mass or relative formula mass, that would be 55.8, because that's the relative formula mass of iron, divided by the relative formula mass of the compound A. So that would be 55.8 plus 32 plus 4 times 16. And then we're going to multiply this by 180, and that gives us 66 milligrams, because we've worked out the ratio of iron in the compound and then multiplied it by the mass of iron in one tablet. So we've got 66 milligrams, and then we're working out B. So we'd have 55.8 divided by 4 times 12 plus 2 plus 55.8 plus 4 times 16. And that gives us the mass, if we multiplied by 210, of 69 milligrams. And so our answer is B. To get the mark for this question, you need to write B on the answer line provided.